Hello everyone and welcome to the channel. So in this particular video we are going to discuss about the Monday MCQ questions which have been posted in the last Monday on organic spectroscopy, right? So many of you appreciated a lot for this particular topic, and I suggest you to please recommend or please tell me what topics you guys want questions on for the next Monday, right? So do tell me that in the comment section below. So yeah, let's start the video. Let's start the solutions. So the first question says that the number of lines that will appear in the EPR spectrum of C6H6 minus. Okay, so that's your radical basically, like that's basically a carbanion, and it is being asked that how many EPR signals you are going to get. So since you have 6 hydrogens over here, using the formula 2Ni plus 1, you can easily tell that how many EPR lines you are actually going to get. So I value for hydrogen is half, and since we have 6 hydrogens over here, so you can put it like this. So 2 into 6 into half and plus 1, so basically you are going to get 7, right? So option B is going to be your correct option for this particular question. Alright, so the next one over here, it says that which one of the following normal modes of ethylene is active in the infrared. Okay, that means which of these is IR active. That's what they are asking. So for IR active mode, the molecule should have, see, if the molecule is has a symmetrical stretching, that is IR inactive. Okay, so symmetrical stretchings are IR inactive. Now if you look upon it, so I'm just writing it over here. Okay, so symmetrical is IR inactive. Okay, so it's IR inactive. So the first option, if you see, it's a symmetrical stretching. Second option is also symmetrical stretching. And the third one, you can see it's not a symmetrical stretching. These two bonds are being stretched. This bond is compressed to this direction, and these two bonds are again getting compressed. So this is basically a asymmetrical stretching. Okay, this is asymmetrical stretching. So this will be IR active. Okay, so option C has to be the correct one. D again is a symmetrical stretching. Two bonds being stretched, two bonds being compressed. So again, it's IR inactive. Those which are IR inactive will be Raman active over here. If there is a like inversion center present in the molecule. Okay, that is very important. So if the center of inversion is there, then IR active mode, like IR inactive mode, are going to become Raman active. Okay, so that you need to understand. Okay, let's go to the next question over here. It says that the lambda max in the UV visual spectrum of the compound from A to C is, it can be easily understood if you look upon the molecules. So over here, you can see that the conjugation is highest in for option number B. So if the conjugation is more, that will increase the lambda max, right? So more conjugation, so your lambda max is directly proportional to conjugation. Okay, conjugation. So obviously option B will be the highest one, right? So B will be highest, so neither option A is correct, neither option D is correct. Option B or C, any of them will be correct. Okay, now you should know that the lambda max of your homonuclear, okay, sorry, your like homoannular diene is always greater than heteroannular diene. Okay, heteroannular diene. What does that mean? It means that if your diene is present in the same ring, that means if the conjugation is present in the same ring, that will have more lambda max compared to that in which the double bond is present in the different rings. So that means A will have more lambda max than C. So option B becomes your correct option for this particular question. Alright, let's talk about the next one. It says among the following, the correct statement is, it says the first statement says that the absorption of radiation shifts to longer wavelength region with the increase in conjugation. The other one says that absorption of radiation shifts to higher energy region with the increase in conjugation. The third one says that intensity of N to pi star transition decreases upon conjugation. The last one says that intensity of sigma to sigma star transition decreases upon conjugation. So you should know one thing, that whenever you have conjugation in the molecule, in that particular case your lambda max increases, right? That's what we know. So that means what? That with the increase in conjugation, your wavelength, okay, the radiation shifts to the longer wavelength. It's pretty simple, right? So lambda max increases, okay, it increases with increase in conjugation, right? So based upon that fact, we can say that with the increase in conjugation, the absorption of radiation shifts to the longer wavelength, and the rest of the factors are not that correct because N to pi star transition generally happens in carbonyl compounds, and that will not decrease with conjugation. Okay, so that is not correct. So yeah, so option A is going to be the correct option for this. Coming to the fifth question, it's again a very simple question. It says which of the following compound exhibit carbonyl stretching at 1770 centimeter inverse. Now, those who have attended my classes, whether it is a live class, whether it is like it's a free class, anywhere, everywhere I have explained this, that at 1770 your gamma lactones gives you that particular value, right? Gamma lactones are like what? Five membered gamma lactones. This is also important. Five membered gamma lactones look something like this, okay? Something like this. So here you don't have that. Here you don't have gamma lactone, but a five-membered gamma lactone is not there. But there is a five-membered similar thing, similar molecule which is quite similar to gamma lactone. So in the gamma lactone, this lone pair of electron comes in conjugation with this double bond, with the carbonyl bond, and that's what makes the carbonyl frequency at, sorry, that's what makes the IR band at 1770 centimeter inverse. Here also same thing is going to happen. The lone pair of this nitrogen is going to come in conjugation of this. So the answer is going to be option number A. No other option is going to be correct. So option A is correct. So whether it is 1770, whether it is nitrogen or oxygen, if the species is quite similar to gamma lactone, it is going to give you absorption band near to 1770 centimeter inverse. Okay, I think that's much clear, right? Okay, so the next one says observe the following statement. Statements are like atomic mass of the isotopes can be obtained from rotational spectra. That's the first statement. The second one says that the separation between the two successive rotational spectra line of the gases NO is 2b. Alright, the third says that the NMR spectrum of compound gave a singlet at 300 Hertz away from the TMS. Using NMR spectrometer operating at 60 MHz, the chemical shift is 3 ppm. Alright, so which of the following is the correct statement? So the third statement is basically a numerical which you can easily do. So since the instrument is 300 megahertz and it is giving you at 60 so the NMR spectrometer is operating at 60 megahertz, so you have to calculate the chemical shift, right? So it's just based upon a direct formula. So the formula for chemical shift is this, that is delta is equals to observed chemical shift in hertz, which is 300. So just put that, so 300 into 10 to the power 6 and divided by the operating frequency. So the operating frequency is 60 megahertz. So 60 megahertz. So if you convert that into hertz, so this is again going to be 60 into 10 to the power 6. So how much you are going to get? So if you cancel this up, so you are going to get 5. So the chemical shift is 5 ppm, not 3 ppm. So the third statement is obviously wrong. Okay. Now you have to check for the other two statements. The first one says that atomic mass of the isotope can be obtained from rotational spectra. Yes, you can obtain that because in the rotational spectra you have moment of inertia, right? And moment of inertia depends upon the reduced mass, mu r square. So it depends upon the reduced mass. So with the change in mass, you can find out the moment of inertia, and with that the rotational spectra is going to vary. So but yes, first statement is correct. The other statement which says that the separation between two successive rotational spectral lines of the gaseous NO is, obviously this is going to be 2b, right? Because between two rotational lines, the separation between two rotational lines is 2b only. Okay, so that's what we know, right? We have already studied in the rotational spectra. So it's a correct statement. So statement number 1 and statement number 2 both are correct. Third statement is wrong. So answer is option number C. Let's go to the next question. It says that an examination of saturated hydrocarbon containing methyl group shows symmetrical and asymmetrical stretching bands in the region of. Now this is a direct question. Okay, we all know that where saturated hydrocarbons which contains methyl group like this kind of group, so saturated hydrocarbon, where does it gives you the symmetrical and asymmetrical stretching of your methyl group of the saturated hydrocarbon, where does it gives, right? So the correct answer for this question is option number A, that is at 2960 and 2870 centimeter. So within that region, two peaks you will get for stretching, for symmetrical and asymmetrical stretching. So talking about this particular question, it says that in the IR spectrum, the carbonyl absorption band of the following compound appears at. So this is nothing but a gamma lactone kind of thing. If you just break down this particular part, or not that, But if you just break this particular part, so you are going to get a gamma electron kind of thing, right? 5-membered ring. Gamma electron gives you at 1770 centimeter inverse. The 6-membered ring is not going to help it in that much. It is not going to alter the IR spectrum that much, since there is no conjugation and other factors are not over here. So the value will remain quite similar to 1770 centimeter inverse itself. So answer will be option number B over here. Looking at the question 9, it says match the following compounds P to S with their carbonyl stretching frequencies from 1 to 5 over here in the IR spectroscopy. P is your acetone. Now we all know that where your acetone is going to bind, right? Like what is the value for acetone? So acetone gives you acetone is nothing but CH3 C double bond O CH3. It's a symmetrical ketone, and ketones gives you at 1700 to 1715 centimeter inverse. So P is going to be matched with this. Okay, so I'm just writing over it. So this fourth one is going to be matched with P. Alright, the next one is ethyl acetate. Ethyl acetate, if you draw this, ethyl acetate is CH3 C double bond O and CH2 CH3. That's what you have. Now this is a ester group, right? And esters give you a peak at a higher wavelength than the ketones, so it's going to give you at 1740 centimeter inverse. So ethyl acetate is like Q is over here. Okay, Q will be matched with this. Next is your acetamide. Okay, that is amide group basically. So if you look upon amide groups, so they are going to give you at a lower wavelength. Okay, amides, acetamide means CH3CONH2. Okay, so acetamide is going to give you at a lower wavelength than the ketone. So this is going to be around 1660 centimeter inverse. Okay, so this is going to be your R. And the last one is acetyl chloride, which is acid chloride, and acid chlorides give you at a very higher wavelength, that is around 1800 centimeter inverse, because carbonyl stretching is around it starts around 1650 centimeter inverse and you get it up to 1800 centimeter inverse. So that is the range for your carbonyl frequencies. So that is going to be like acetyl chloride is going to be this. Okay, so this is going to be S. So based upon that, you can say that option number C is the correct option, right? Acetyl chloride, if you don't know, so this will be CH3CO Cl, right? So that will be acetyl chloride. Alright, so let's take question number 10 now. It says that at the room temperature, which of the following molecules are expected to give 5 NMR lines in the proton decoupled carbon 13 NMR spectrum? That means we need to find out that which of these contain 5 types of carbon. So let's quickly do that. So in the first option, if you see, it's a symmetrical molecule along this line, okay, along this this particular dotted line. So if I number them up like this, so if this is a type of carbon, this is also A type of carbon. This is B, this is also B, this is C, this is also C, this is E, this is D, and this is E. So you have 5 types of carbon over here. In option number 2, if you see, so this is A, this is also A, okay, because both of them have same chemical environment. This is B, this is C, and this is D. So only 4 types of carbon. So option 2 is cancelled out. In option number 3, if you look upon, so basically over here, if you see, so yeah, it's a axial and equatorial kind of thing. So basically, yeah, so here what you have to look upon is whether you can like whether this is a symmetrical thing or not. Okay, so that's what you have to see. So this is A type of carbon. Okay, this is B type of carbon because there is no other carbon which is quite similar to that. This is C type of carbon. This is going to be different. This is D and this is E. Okay, and the other ones will obviously be different because this is C, which is in between of these two groups. Okay, this particular carbon, if I talk about, so this is not that kind of group which is in between of two like carbon which contain methyl group. So the chemical environment over here is different. So this is going to be the F type. So obviously you got more than 5 types, so you can just cancel out. You don't have to look upon it further. Okay, talking about option number 4. So here again it's a symmetrical molecule. I can just symmetrically divide it. So how many types of groups I have? So carbon A, carbon A, carbon B, carbon B. This is C, this is C. Okay, this is symmetrical along this as well. So C, C, this is also C, this is also C. Only 3 types of carbon. So you can also cancel out this option as well, right? Option 4 is going to be same as option 2, so you can cancel out that as well. And in option number D, if you see over here, If this is carbon A, this is carbon B. Okay, so again, this is going to be carbon C, and this is going to be carbon D basically. Okay, so if you draw this in this form, okay, in this particular form, now you can easily answer it. Okay, see, your molecule become a symmetrical molecule. This is A, this is also A, this is B, this is also B, this is C, this is also C, this is D, and this is also D. So you got just 4 types. Okay, so if you look upon it, basically the answer is it should be only A. So there is no option like that, but yeah, the correct answer has to be only option A. Okay, there is only option A, which is giving you 5 types of carbon. Okay, so option A should be the correct answer. Okay, if you try to see the third one similar to that, so here you have okay, so okay, one to axial equatorial is going to be cis, right? So both of these are actually cis, and this has to be trans. Okay, so this is above the plane, and this is going to be below the plane. Sorry, not here, but yeah, at the third position, this has to be below the plane. Okay, yeah, now you can draw this basically. So if you look upon it, so this is going to be symmetrical along a axis of rotation. You can rotate it along this axis. So this carbon and this carbon can be rotated and can be interchanged their position. This is going to be B, and this is also going to be B. Okay, this is C, and this is also C, because they can interchange, and this is D, and this is E. Yeah, so they are 5 actually. Okay, so I did mistake over here. Option A is going to be the correct answer. Okay, so yeah, if you have any molecule which is in the form of your cyclohexane in the chair form, first of all you have to draw that molecule in the planar form. Try to draw the stereochemistry based upon axial and equatorial thing, and then you have to check. Okay, since both of these were 1 to axial equatorial, so they were cis, right? No? So since they were cis, so that's why I have done it like that. So only 4 types of carbon we got in this case. Yeah, so option 1 is correct option. All right. Okay, let's look for question number 11th. It says that an organic compound Q exhibit the following spectral data. The data is given to you. IR you are getting at 1760 centimeter inverse. NMR you are getting at these are your NMR. So 1, 2, 3, 4, and okay, 4 peaks. And yeah, so you are getting 4 peaks basically. So 1760 centimeter inverse is going to tell you that it's a like obviously it is going to be a ester, right? It's going to be a ester. It's not a conjugated carbonyl. uh, it's not a conjugated ketone basically. So if you look upon it, so conjugated ketone will give you a lower frequency. So option C you can easily cancel out, right? Now looking upon the options, you can see you can even say that it's not a, yeah. So if you look upon it, if you look, yeah, so IR is going to help you in that way. Now taking the proton NMR, okay, so in the proton NMR, you can see that 1, 2, 3, 4 signals you are getting. Now if you see how many types of protons you have, so in A, if I name it like this, so here I'll be having 1 hydrogen, here I'll be having 1 hydrogen. Okay, so this is A, this is going to be B, this is going to be C, and this is going to be D. So 4 types of hydrogen over here. In this one again I'll be having A, okay, and this hydrogen and this hydrogen. So this is going to be B type of hydrogen, C type of hydrogen, and D type of hydrogen. All right, option D again will have the similar kind of thing. So 1, 2, 3, 4 types of hydrogen. All right, so fine, let's take the chemical shifts now to understand it. So I'll just erase whatever I have written as A, B, C, D. So I'll just erase that. Okay, so all right, so now you can just look upon the chemical shifts. So the best chemical shift, the best way which is going to help you to understand is for the methyl group, the methyl group which is all alone. Okay, so 3 hydrogen and yeah, so 3 hydrogen group. Okay, so 3 hydrogen is over here, and this is again 3 hydrogen singlet. That is going to give you for that alone methyl group. Okay, so OMe is not that. Okay, so OMe has a little higher chemical shift. It is not going to give you at 2.1. Okay, so 3 hydrogen singlet is going to tell you that this is not OMe. So you can cancel out option number D. Okay, so we have just taken the isolated methyl group basically. So that methyl group is obviously not going to be OMe. If it is OMe group, In that case it will give you around 2.9 or 2.8 or 3 basically. So that's not here. Okay, so you can just cancel out option D. Now you are just stuck between option A and B. If you look upon both of them are quite same. The only difference is between these two hydrogens, okay, whether they are cis or they are trans. That's what you have to decide. So that you are going to get on the basis of your J coupling. Okay, so if they are going to be cis, in that particular case their coupling constant is going to be, yeah, so based upon the coupling constant you can tell. Okay, so the coupling constant for this particular hydrogen is quite high, that is 16.0 hertz. That's telling you that this is a trans coupling, not a cis coupling. That's one of the thing. um, the other thing which is over here is that the chemical shift of this particular hydrogen, which is over here one hydrogen and its multiplicity is yeah, it's a multiplet, right? So it is giving you at 5.1. That means this particular hydrogen over here is, again, it's a trans one. Okay, so it's in the chemical environment of this methyl group. Basically the best way to understand cis and trans is on the basis of J coupling. Okay, so the J coupling of the trans hydrogen is quite high than the cis coupling. Okay, so that there is a rule, I just forgot the name. If you remember the name, do let me know in the comment section. But yeah, there is a rule that if there is a trans coupling, that is given more priority, or the trans coupling has a higher value than the cis coupling. Okay, so option A will be the correct option based upon that. Okay, so the next question says that the ketone on the treatment with bromine in the methanol gives the corresponding monobromo compound X having molecular formula C5H9BrO. The compound X, when treated with NaOMe in the methyl OH, produces Y with the major as the major compound. Okay, so the spectral data of the compound X are the proton NMR. You having 1, 2, 3 signals. Okay, so you are having 3 signals over here. So let's see in which options you are having three types of proton. So in option A, if you see, there is a one type of proton, there is a B type of proton, C type of proton, and D type of proton. So option A you can cancel. In option B, again, A type of proton, B type of proton, C type of proton, and D type of proton. So option B also you can cancel. In option C, you have A type of proton. This is also A type of proton. This is B type of proton, and this is C type of proton. So three types of proton you have in option number C. Here again you have A type of proton, A type of proton, B type of proton, and C type of proton. So three protons here again. So you have to choose between option B and C. Sorry, option C and D, which is going to be the correct option over here. So that is going to be decided by the multiplicity of the peaks. So whether you have a 3 hydrogen singlet or not. Okay, that's what you have to go see. So this, if this is true, then you will get 3 hydrogen singlet somewhere. So is it there or not? Is that there or not? So there is no 3 hydrogen singlet, right? And if this is true, in that particular case you will get 2 hydrogen singlet. Okay, so 2 hydrogen singlet with a high chemical shift that you have at 4.03 2 hydrogen singlet. Okay, so that is telling you clearly that option D is the correct option, not C. If C would be correct, you would have got 3 hydrogen singlet with a chemical shift around 2.1 something, right? So option D is going to be the correct option for this. Alright, so in the second part, you have to react the major product Y, right? So how product Y is getting formed? When this particular D is going to react with NaOMe, right? That's what it is given in the presence of MEOH, right? So you guys have to tell me in the comment section that which name reaction they are actually talking about. So what this is going to do, this is going to take like hydrogen from here, forming a double bond, like alkane will be formed, and later on your OMe is going to come and it is going to bind at this particular place. So what product you will get? You will get option number C as the final product. Okay, so you have to show the mechanism, what is happening in this particular reaction. Okay, and what is the name of that reaction, that you have to tell me in the comment sections below. All right, okay, so let's go to the last question. It says that the correct pair of proton and 31p NMR spectral patterns for your CHF PCl2, right? So you have PCl2. So that's what you have. So what will be the pair of your proton and your phosphorus NMR? Okay, so basically this is your proton. This is like it is 1 and 2 bonds away from all these phosphorus. Okay, so this is 1 and 2 bonds away from this phosphorus. So this is going to the proton signal is going to get splitted by this phosphorus. So using the formula 2Ni plus 1, this is how it is going to split. So there are two phosphorus. So proton, who is going to split that proton? Phosphorus is going to split that proton. So 2 phosphorus, I value of phosphorus is half and plus 1. So if you solve this, you will get 3. So there should be a triplet which you are going to get. Okay, so you are going to get a triplet in the case of your proton, right? And yeah, and before that triplet, this fluorine is also NMR active, right? So it is also going to split that. So basically I'll show you once again that what actually is happening. This is because of phosphorus. Okay, so this is because of phosphorus. Now because this is away from it, right? Now talking about fluorine, so the one who is more electronegative is going to split first. So fluorine is going to split it according to 2Ni plus 1. So there is one fluorine, so I'm just writing F. So 2 into 1 into half and plus 1, if you use that, so you are going to get a doublet. So basically one line of your hydrogen is going to split up into 2 because of this fluorine. Okay, and then these lines are going to split into 3 because of phosphorus. Okay, so this is how the pattern you are going to get. Okay, so this is called as um, triplet of doublet. Okay, so that's doublet of triplet. So that's what you will get. Okay, so that's sorted out for for the proton. When you talk about phosphorus, so first who is going to split that phosphorus? So first this fluorine is going to split that phosphorus in this using this formula 2Ni plus 1, and here I of F will be written and multiply by 2Ni plus 1, and this will be from the hydrogen. So first this fluorine is going to split and then hydrogen is going to split. So 2 into 1 fluorine and half is the value of fluorine, and into 2 into 1 hydrogen and half is the value of hydrogen. If you solve this, basically you are going to get 2 into 2. So how your phosphorus NMR is going to look? So one line of your phosphorus is going to split into 2 because of fluorine, and then individually both of these lines are going to get split into 2 because of the hydrogen. Okay, so that's how the peaks are going to look. So if you look upon the options, option number C resembles it quite well, and that is going to be the correct option, right? So I hope this is quite clear, and these were the 14 questions which I have given on organic spectroscopy. I hope you guys understood the solution and you guys like the video. If you guys have any suggestion, if you guys want any specific topic to be taken the next Monday MCQ, you can tell me in the comment sections below. And that's all from my side, guys. Thank you so much for watching. Do let me know in comment section about your suggestions, about what you feel like. If you have any question you are not able to understand, ask me out in the comment section below. So that's all from my side for this particular video. See you in the next video. Till then, have a great day. Bye bye.